All right, today we're going to look at calculating limits using the limit laws. So our limit laws say, suppose that C is a constant and the limit as x approaches a of f of x and the limit as x approaches a of g of x exist. So in order to use these limit laws, these two limits must exist. Okay, and I'm going to quickly go through our 11 limit laws. The first one says the limit as x approaches a of the quantity f of x plus g of x is equivalent to splitting up those limits. So I could say the limit as x approaches a of f of x plus the limit as x approaches a of g of x. So notice what we did here is we kind of split this up and we took two different limits. We used it's called our sum law, okay? And the same is going to apply for the difference limit law. The limit as x approaches a of the quantity f of x minus g of x can be equivalent to the limit as x approaches a of f of x minus the limit as x approaches a of g of x. The next one we're going to talk about is if we have a constant c. So the limit as x approaches a of the quantity c times f of x equals, I could pull that c out front and say that constant times the limit as x approaches a of f of x. The fourth limit law we're going to talk about is the product law. The limit as x approaches a of the quantity f of x times g of x is equivalent to taking the limit as x approaches a of f of x and multiplying it by the limit as x approaches a of g of x. My next limit law is going to be the quotient limit law that says the limit as x approaches a of f of x divided by g of x is equivalent to taking the limit as x approaches a of f of x and dividing that by the limit as x approaches a of g of x. Now, one thing we have to know is the limit as x approaches a of g of x can't equal 0 because I can't divide by 0. The sixth limit law we're going to talk about is the power law, and that says the limit as x approaches a of f of x raised to the n power is going to be equivalent to taking the limit as x approaches a of f of x and taking that quantity and raising it to the nth power. Limit law 7 says the limit as x approaches a of c equals c. So the limit as x approaches a of a constant is just going to equal that constant. Limit law 8 says the limit as x approaches a of x will equal a. Limit law 9 states that the limit as x approaches a of x to the nth power is going to be equivalent just to a to the nth power. Limit law 10 is going to state that the limit as x approaches a of the nth root of x is equivalent to the nth root of a. And one thing we need to note here is if a is even, we are going to assume that a is greater than 0. And then the last limit law we're going to talk about today is the limit as x approaches a of the nth root of f of x is equivalent to taking the nth root of this entire quantity, the limit as x approaches a of f of x. And we're going to kind of look at this in two different ways. And I'll refer back to these limit laws, 1 through 11. We're going to look at it two ways. We're going to look at it graphically, and then we're going to look at it algebraically. So we have this graph here, our first example. It says the graph of the functions f and g are given below. Use the graph to answer the following questions. So right here I have the graph of f, and then I have the graph of g. And this asks for the limit as x approaches -2 of the quantity f of x plus g of x. Well, the first thing we're going to do is we're going to use our limit laws. And our limit laws, we could use our sum limit law and split this up to say the limit as x approaches -2 of f of x plus the limit as x approaches -2 of g of x. And then we're going to have to go to our graph, and we're going to look at, well, what is the limit as x approaches -2 of f of x? Here's f of x, and we're looking at, here's 0, 0, so we're looking at -2. As x approaches -2, f of x is approaching 0. So we're going to say 0 plus the limit as x approaches -2 of g of x. So we're going to go to g of x, -2. It looks like x approaching -2, f of x is approaching +1. So the limit as x approaches -2 of the quantity f of x plus g of x is 1. Okay. We're also going to look at, well, what happens if it asks for us to use the product property, the limit as x approaches -2 of f of x times g of x. Using our product property, we could split this up and say the limit as x approaches -2 of f of x times the limit as x approaches -2 of g of x. And we already evaluated both of those. So the limit as x approaches -2 of f of x, we already said was 0. And the limit as x approaches -2 of g of x, we said was 1. So when I multiply those together, I get 0. Example 3 asks us to use our quotient laws. So the limit as x approaches 0 of f of x divided by g of x. We're going to use our quotient law and say this can be split up to saying the limit as x approaches 0 of f of x divided by the limit as x approaches 0 of g of x. Okay, and we're going to take a look at both of these. So the limit as x approaches 0 of f of x looks to be 2. If we look up here, so here's 0. Looks like f of x is approaching 2. And the limit as x approaches 0 of g of x looks to be 0. Well, what is 2 divided by 0? We're not allowed to divide by 0, so does that limit exist? Does not exist, so we'll put D and E. Let's look how 3 and 4 are different. It's still the limit as x approaches 0, but now instead of the function x divided by the function g, I'm taking the function g divided by the function x. So is this still going to not exist? Let's see. We're going to take the limit as x approaches 0 of g of x and divide it by the limit as x approaches 0 of f of x. That's going to give me 0 divided by 2. Well, 0 divided by 2 is 0. So the limit as x approaches 0 of g of x divided by f of x is 0. And that's okay. All right. So let's look at doing some of these algebraically. Let's use the limit laws to evaluate this next statement. So it says the limit as x approaches 2 of the quantity 3x squared plus 5x minus 3. And it asks me to use my limit laws. Okay, so we want to be really careful here. When it asks me to use my limit laws, I must actually use them. Okay, so I can't just take 2 and plug it in. That would be nice, and we might get to that, but right now it is asking us to use our limit laws. So we're going to split this up. And first thing I notice is I have a sum and a difference. So what I'm going to say here is the limit as x approaches 2 of 3x squared plus the limit as x approaches 2 of 5x minus the limit as x approaches 2 of 3. Okay, now notice I have a constant times a variable. So I could pull that constant out front and say 3 times the limit as x approaches 2 of x squared plus 5 times the limit x approaches 2 of x minus the limit as x approaches 2 of 3. Now notice here I have x and x. Okay, and that is one of our limit laws we talked about. Okay, so from here I'm going to actually start evaluating. Okay, so I'm going to have 3. The limit as x approaches 2 of x squared, I'm going to be able to say, well, I could just put that 2 in and say 2 squared. So it's going to be 3 times the quantity 2 squared plus 5. The limit as x approaches 2 of x is 2 minus the limit as x approaches 2 of 3, well, that's a constant, so that's just going to be 3. So we get 3 times 4 plus 5 times 2 minus 3, which gives me 12 plus 10 minus 3, 12 plus 10 is 22, 22 minus 3 gives me 19. Okay. Notice the use of my equal signs. Please make sure you continue to use equal signs going all the way down. This is a work that I'm going to want to see if it asks you to use the limit laws. Okay. Now, if sometimes we're going to be able to use something called the direct substitution property. Okay. If f is a polynomial or a rational function and a is in the domain of f, then we could say the limit as x approaches a of f of x is f of a. Okay? And we need to be really careful to make sure that a is in the domain of the function. Okay? Let's look at an example. Look familiar? Okay. Notice here, 2 is in the domain of this function. Since 2 is in the domain of the function, we could use the direct substitution property and just say, well, this is equivalent, the limit as f approaches a of f of x is equivalent to f of a. So we could just say this equals 3 times 2 squared plus 5 times 2 minus 3, which still gives me 19. Okay. Let's look at an example where direct substitution maybe isn't going to work right away. Let's look at example 7. It says the limit as x approaches 3 of of x squared minus 6x plus 9 divided by x minus 3. Why can't I just use direct substitution? We can't use, I'm going to call it DSP, direct substitution property, because 3 is not in the domain okay? If I plug 3 in here, what happens? 3 minus 3 equals 0. Can I divide by 0? No. So, what are we going to do? We are going to first manipulate the function. Remember, we're looking at the limit as I approach 3. I'm not asking what is the function when x equals 3. I'm asking what is the limit as I approach 3. So what I could do here is maybe factor my numerator. If I factor my numerator, that still gives me the limit as x approaches 3 of, let's see, what is that? X minus 3 times x minus 3 over x minus 3. Well, that's nice, because those two can cancel, and that gives me the limit as x approaches 3 of x minus 3. Well, now 3 is in the domain, and, oops, let's make sure we carry our equal sign down. Okay, notice I forgot that. That's not okay. Make sure you keep on putting that in. So the limit as x approaches 3 of x minus 3 is 3 minus 3, which equals 0. Okay, so the limit as x approaches 3 of this function is 0. That doesn't mean that f of 3 is 0. So make sure you're getting that, the difference that we're talking about there. Okay, that's going to end the lesson for today. When I see you next, we are going to move on to talking about the squeeze theorem, which is the end of 2.3, and then we'll move on to 2.4, which is continuity.